This is EGME-331 Solid Mechanics Prerequisite video series, and in this video we'll be discussing about bending moment diagrams. Bending moment for a particular section may be defined as the sum of moments about that section of all external forces acting to one side of that section. Bending moment diagram, in short BMD, is a graphical representation of the variation of the bending moment on a segment or the entire length of a beam or the frame. The bending moments at any point are calculated by multiplying the magnitude of the external forces, that means the loads or the reactions, by the distance between the point at which the moment is being determined and the point at which the external forces are being applied. Coming to the sign conventions, a positive internal bending moment causes compression in the top fibers of the segment, that is clockwise on a left facing cross section or counterclockwise on a right facing cross section. So as a sign convention, the positive bending moments are drawn above the excentroidal axis of the structure, while negative bending moments are drawn below the axis. So let's discuss the bending moment diagram plotting procedure with the help of an example. So just like we saw in the shear force diagram plot, we need to determine the support reactions. We need to specify the origin and then sum of the forces vertically to determine the shear force, and then sum the moments at the sectioned end to determine the bending moment. And this would eliminate the shear force from the moment equation. Let's take a look at an example. Consider drawing the bending moment diagram for the cantilever beam shown here, supporting a concentrated load of 5 pounds at the free end 3 feet from the wall. The first step is to draw the free body diagram of the structure. Next, we calculate the reaction force, just like we did for the shear force diagram. Here, at the support at B, we have three reactions, the B sub Y, B sub X, and the moment M sub B. From here, we can get the three equilibrium equations as shown here. Now we need to add the internal forces. For this, make a cut and add the internal forces NV and the moment M using the positive sign convention. Depending on the number of the loads, again, you may need multiple cuts. The next step is to find the shear force equation, as we saw in the earlier video on shear force diagram. Once we have the shear force equation, we move on to the next step. Here we find the bending moment equation. For the moment, find an equation of the shear that is x distance from the origin. For this applies for each cut. That means here x is measured from the left using the sum of the moments equation. Find the expression for the moment m. So you could choose the moments about the end point where the load is applied, or you could do it at the moving point x. So that's your choice, but both take the same effort for this problem. So let's choose the left hand side where the 5 pounds are being applied. So we have the moment equation in terms of shear force, and we can estimate the moment to be a function of x will be negative 5 pounds multiplied by x. Here the negative sign indicates that the arrow goes the other direction. Once we have the bending moment equation, next step is to plot the equations on a bending moment diagram. Since the function for the bending moment diagram is linear, the bending moment diagram is a straight line. Thus, it is enough to use the two principal values of the bending moment determined at x equals 0 feet and x at 3 feet to plot the bending moment diagram. As a sign convention, the negative bending moment diagrams are plotted below the neutral axis of the beam, while the positive bending moment diagrams are plotted above the axis of the beam.